Hi.
Ouais.
Good morning, ladies and gentlemen. Are you ready? Okay, thanks. So my name is Joseph Catalano. I am the CEO of the company CWANTIC. And today I am very pleased to give this presentation about the RCC-MRx code and MetaPiping. So here is the agenda for the presentation. Just a few words about the company CWANTIC. And then we'll come to the core of the presentation, the RCC-MRx code, and in particular, the implementation in the MetaPiping software. This will be followed by a case study presented by Mr. Noé, and finally, a few words of conclusion. So the company CWANTIC was founded in 2022 in Lyon with the goal of developing innovative software for the nuclear industry. And currently we develop two software, MetaPiping for pipe stress analysis and MetaStructure for piping support and seal frameworks. The development is based on 5 pillars: modular architecture, easy CAD-like modeling, robust nuclear qualification, of course, and open to Python. And finally, 100% compatibility with pipe stress, mostly for historical reason, I would say. So let's come to the core of the presentation, the RCC-MRx code. So the RCC-MRx code is a French code that provides rules for the construction, for the design of high temperature equipment. And it's particularly aimed at applications like high temperature SMRs. As you know, they have many benefits. The ability to reuse spent nuclear fuel, improved efficiency compared to the current plants, Gen 3, because of the higher temperature, of course. And however, it comes with many complex challenge. Well, the first challenge is to select the materials able to resist such high temperature. And the other big challenge is to assess the creep and creep fatigue interaction. And as far as I know, the RCC-MRx code is the only code currently that provides a full set of rules to address those issues. And that's the reason why we decided at CWANTIC to implement the code into our software MetaPiping. So I'm not going to give you a lesson about the RCC-MRx code. It would take hours and hours, but just two very important topics addressed in the RCC-MRx code. The first topic is a creep and creep plus fatigue interaction. And in fact, for steel, creep is significant above a temperature of about 450 degrees. And creep can lead to progressive deformations and then to rupture. So it has to be drastically limited. And in the RCC-MRx code, this is assessed by means of two numbers, the creep usage factor U and the creep rupture factor W. We have also to take into account creep for the fatigue analysis, because there is an impact of creep on the fatigue resistance of the material. And this is assessed in the code by means of the interaction diagram, so fatigue and creep. Another important topic in the code is what we call the elastic follow-up phenomena. As you may know, pipe stress analysis is based on linear calculations. However, that can be unconservative and wrong if the system is unbalanced. I'll just give you a little example to illustrate that. In the first case, we have a perfectly well-balanced system. Part A and B have the same cross-section. So if you apply a loading, for example, displacement delta L, the strain calculated elastically will be the same as the real strain. Okay? Now, the second case is an unbalanced system. The cross-section of part A is much smaller than the cross-section of part B. And if you apply a loading, for example, a displacement, in fact, the strain calculated elastically will be unconservative. It might be much less than the actual strain. So if you want a sound and precise analysis, you have to take this phenomena into account. And the RCC-MRx, the code, the RCC-MRx code provides actually some methods to take this phenomena into account by means of what we call the elastic follow-up factors for monotonic and cyclic loading. Okay? So let's have a look now at the implementation of the code into MetaPiping. But the first thing we had to do is to build a library of materials. Because for the RCC-MRx code, we need a lot of data. You need the creep, fatigue interaction, the creep laws, the interaction diagram, and so on. So it's practically impossible to enter all this data for the user. So we decided to build a library with most materials used. And for the user, it's pretty easy. You simply have to select the specification, and all the data are readily available. The second thing we have to do is to define the geometry and the loading. Well, that's pretty similar to what you have in other piping codes. There is no big difference. However, you have to describe the steady-state conditions accurately, in particular the duration. It's very important for creep. And the second thing you have to pay attention to is the definition of the transient conditions, the transients. And in MetaPiping, this is done by means of what we call a load set. And the load set have to take into account the fluid transients. When you have a temperature of fluid transients, of course, you have thermal gradients across the thickness, and they have an impact on the fatigue, the cyclic analysis. And this is an example, for example, of steady-state conditions, 650 degrees, with two transients, startup transients, cool-down transients. And in MetaPiping, that's pretty easy to define those transients, and automatically MetaPiping will take the thermal gradients into account in the cyclic analysis. Once the loadings and the geometry and the materials are selected, we come to the calculation according to the RCC-MRx code. And the first thing that is carried out in MetaPiping is the check of significant creep. And that is performed according to Appendix A331. The next step is the verification of the type P damage. So what we call a type P damage is a damage that is due to the application of a steady or almost steady loading. For example, thermal expansion, dead weight, and so on. And to do that, MetaPiping calculates what we call the monotonic elastic follow-up factor, RM, and the abatement coefficient, G. And using those numbers, we are able to evaluate the stresses according to the CMS1 method. And then, of course, to make sure the damage are acceptable. If creep is significant, we have also to evaluate the creep usage factor, U, and the rupture factor, W. And we have to do that for all the steady-state conditions. The creep usage factor, U, has to be lower than 1 minus delta UA. And the calculation of delta UA is pretty complex. It's really complex. It involves a lot of iteration. And in MetaPiping, this is done in the most I would say, rigorous way without any simplification. Okay? The next step is the verification of type S damages. So type S damages are about stress variations. And in fact, there are 3 different failure mechanisms we have to verify. The first failure mechanism is progressive deformation. Then the second, fatigue. And the last one is creep rupture. Okay? So for the first mechanism, progressive deformation, MetaPiping will calculate the stress range that we call Q between all the possible states, all the possible load sets. And based on the maximum value of Q combined with the maximum primary stresses PM and PM plus PB, we determine the equivalent efficient stresses P1 and P2 that has to be limited to a maximum value depending on the material and the temperature. Okay? If creep is significant, we also have to verify that the plastic plus creep strains during the wall level aid loadings is limited to a value, epsilon delta P1 and epsilon delta P3, that also depend on the material. So now we come to fatigue, okay? So the way fatigue is addressed in the RCC-MRx code is pretty similar to what you can find in other code like RCCM, ASME. So of course you have to determine the maximum, the peak stress variation between all the states, the stress states that we call SN and SP. And as illustrated in the diagram below, okay, you have to figure out what is the maximum stress or strain variation between the load sets, enter the maximum variation in the fatigue curve, and then based on that, calculate what we call the cumulative usage factor using the minor rule. Okay, so that's pretty usual, I would say. There is, however, a big difficulty when you do that is to avoid over-conservative counting of cycles. And this is illustrated in the figure here below. Let's imagine that we have a steady state P1 and a transient that occurs 100,000 times. You have another steady state condition, P2, with another transient that occurs 100,000 times. So I have a quiz for you. How many cycles can you form between the peak value, so the delta epsilon? Well, the first obvious answer is 100,000. Unfortunately, that's wrong. Sorry. Because the number of transitions between state P1 and P2 is actually limited to 5,000. So you can see that this has a huge impact on the fatigue analysis. And what we have done in MetaPiping is to identify the transitions between steady states conditions in order to take into account this issue. Okay? Then we come to creep. Sorry. And if creep is significant, we have to check the strain due to creep in the holding time that follows a cycle, a load cycle. And we have to take it into account in the fatigue analysis as well, to have to add the creep strain to the elastic and plastic strain. There is another number we have to verify, to calculate, is what we call the creep rupture damage, W, during the holding times. And to do so, in MetaPiping, we take into account the beneficial effect of relaxation. Okay, because in most software, we simply take the maximum value and we consider it's constant, and then we have a quite over-conservative result. Here, we really take into account what you can see in the diagram, the fact that the stress will decrease due to relaxation. So that's a very accurate analysis, actually. Finally, when you have the V, so the fatigue, usage factor, and the creep damage, the creep rupture factor, you have to verify the interaction. So in the x-axis, you put V, the fatigue usage factor. And on the y-axis, you put W, the creep rupture factor, and you have to verify that the point is inside the green area. That's what we call the fatigue plus creep interaction. Okay, you see that all this is pretty complex. It's a lot of calculations. But that's not the most complex issue we have to solve, because the code asks you to figure out what is the worst history, what is the worst succession of load sets and holding times in order to maximize the V plus W set. That's an extremely complex issue. And in MetaPiping, we have developed a special algorithm, completely original and we think innovative, that allows to determine this loading history in order to maximize the fatigue plus creep effect. Okay? So now I let my Mr. Noé speak about a real-life application of the MetaPiping software and the RCC-MRx code.
Merci beaucoup, Joseph. Alors, je vais parler en français, je suis désolé. Donc, merci, Joseph, de nous avoir invités sur le salon de WNE pour présenter donc, un cas d'utilisation sous le logiciel MetaPiping de calcul au RCC-MRx. Et donc, on va vous présenter un cas pour le projet de Stellaria, qui est le développement d'un réacteur à sel fondu et à neutrons rapides. Donc moi, je suis Xavier Noé, donc j'ai oublié de me présenter. Je suis référent technique en calcul pour tout ce qui est calcul de tuyauterie pour l'entreprise Prix de Plus 2, qui s'occupe sur ce projet en partenariat avec Stellaria du développement de la conception et du dimensionnement. Stellaria s'est entouré de plusieurs partenaires donc, pour mener à bien ce projet, donc, que ce soit CGD pour tout ce qui est analyse de fabricabilité, Six Sense Next pour tout ce qui est le génie civil et Technetics pour tout ce qui est les joints. Qu'est-ce que donc le projet de Stellaria? Donc c'est un projet donc comme je disais donc qui est né donc c'est une start-up française que vous pourrez retrouver sur le salon. Qui est né d'un projet entre le CEA et Schneider Electric pour un réacteur à sel fondu de 2 fois 250 MW et qui permet donc de renouveler 100% du combustible lors de son utilisation et permet aussi de brûler les déchets de longue vie au sein du réacteur. Donc là, vous pouvez voir donc, à droite donc, le réacteur qui est en cours de développement donc, en partenariat donc, entre nous et Stellaria. Donc actuellement, les études APS, donc tout ce qui est preliminary design, ont été finies. Donc on est sur les études APD pour ce réacteur. Et en plus donc, du réacteur est développé donc, une expérimentation critique qui s'appelle Alvin et Mega Alvin, donc pour lequel je vais présenter donc, les calculs RCC-MRx, qui est le prototype. Et donc nous, au sein des Prix de Plus 2, donc, sur ce projet, on s'occupe de tout ce qui est développement du réacteur, en partenariat toujours donc, avec Stellaria, du réseau primaire, du château de plomb, de tout ce qui est réseau secondaire, et de l'implémentation du génie civil et des protections, des différentes protections. Donc le cas d'étude qui s'est fait sous RCC, sous MetaPiping, c'est le calcul du réseau primaire de méga Alvin, donc avec des températures qui vont à plus de 600 degrés et une pression d'environ 20 bars. Donc on a pu établir grâce au logiciel de CWANTIC les dommages de type P avec et sans fluage. Et donc on est en cours après pour la suite. Voilà. Donc là on peut voir à gauche donc, le 3D et à droite donc, la modélisation que l'on obtient sous MetaPiping avec les différentes conditions limites. Et le cheminement avec des thermal loops, donc des lyres, qui ont déjà été mis en place, puisque là c'était après itération, et les différents supportages qui ont été mis en place. Donc ce qui est bien avec donc, le logiciel de CWANTIC, donc de MetaPiping, c'est que pour le calcul sous RCC-MRx, c'est la facilité de pouvoir établir toutes les équations qui sont faites presque automatiquement et avoir aussi tout le détail de tout, comme il a expliqué Joseph, tous les facteurs qui rentrent en compte dans le calcul de ces équations, donc que ce soit le facteur d'usage, l'effet ressort, voilà. De quoi ? Le coefficient d'abattement, le coefficient G, le coefficient d'abattement, qui sont plein de coefficients qui rentrent en compte dans les différentes équations, que ce soit donc pour les dommages de type P, donc le coefficient d'abattement, le coefficient G rentrent beaucoup en compte dans les contraintes de type PM plus PB. Et nous avons en bas à droite donc après le calcul en fluage en dommage de type P avec fluage, donc pour les lignes à 650 degrés, donc là où on va calculer les UAC et les delta UA. Voilà, les différentes choses comme ça. Je vais laisser la parole à Joseph qui va présenter donc le fonctionnement du logiciel.
Yeah, thank you. I would like now to show you a short demo about how the MetaPiping software works or how it looks like. So that's the next. Yeah. Ah non, sorry. Vous pouvez lancer la vidéo. So okay, that's a short video. You can see the project. In this case, it's a full project with the piping systems and the support. Here you can model the supports with meta structure. The supports are connected to the piping, so that will be let us perform a coupled analysis, and there we come back to the piping study with the coupled support. Here you can see the complete systems. And we have a lot of tools just to define the geometry, to show the support. Here we have the definition of the load cases, static load cases, fluid transient, and you can see how it is. So we have two loops, the cooled and the hot leg, sorry. Here we can define the temperature transients. You see how easy it is. Then we have all the combinations for the stress verification, so the type P damage usually. And here we have the definition of the load sets. That's for the cyclic analysis, for the fatigue analysis. So we define everything, all the moment cases, thermal transients. Once everything is defined, we can go to the analysis and display, for example, in this case, we can display the mode shapes, the results for the dead weight analysis, with all the detailed results on the right with the text report. On the left, you have the graphical display. Okay, you can see practically all the numbers you need for the detailed analysis. Yeah, this is about fatigue. Fatigue analysis. You have the modal extraction, the detailed results, deflected shape, internal forces and moment, the reactions, all the detail of the stress analysis. Here the SIF, the transients, or the thermal transients with the delta T1, delta T2 as a function of time. So that's pretty detailed. And okay, I'm going to show you now mode shape with the animation just to have insight how it vibrates. So you see, you have all the graphical tools to manipulate the model, to check the results. That's pretty easy. Okay, stop. So next, we'll check another combination, dead weight plus pressure plus earthquake. And so that in this case, we have the type P damage with the abatement coefficient. We are going to display the abatement coefficients here. Of course, before you can show the internal forces and moment thanks to moment diagram on the left and the numerical values on the right in the table that you can sort, export to Excel and whatever. So you see how easy it is. We can also display the reactions, obviously, for the support analysis. And maybe the most important, the stress ratios. So on the right, you see all the details, number that you can double check. And of course, on the left, you have a column map. Something very, very useful, in fact, is the detailed FEA, finite element analysis of a component of the piping. So here we are going to perform evaluation of the limit load thanks to nonlinear analysis. So grade deformation, grade displacement, and nonlinear elastic plastic material. So that way you can mesh the elbow. look at the deformation, so you can notice the ovalization effect. Well, it's very much magnified in this case. And here the stress. You can hide some parts of the elbow just to see inside to verify the stress distribution and make sure that we are below the plastic moment. That's kind of a limit load analysis. Okay, this feature is available for tees, for reducer, and so on. And it will extend it in the next version, of course. Here you can visualize the abatement factor, G. Okay. The detailed fatigue analysis with the maximum ratio and all the numbers, the usage factor, the interaction V plus W, all the details on the right. And of course, you have also detailed reports. And you can sort the tables. And you see in red, you have everything that exceeds the allowable, the limits. Now we have the same for the creep, in particular the delta UA. I told you about the calculation. And you see here, the delta UA is mainly important at the elbows. Okay. And yeah, we have also in MetaPiping a layer management that allows to show some part of the piping. You have very complex piping. It's very easy to show and hide some part of the piping. Here, we'll come back to the support analysis, because here what we have performed is a coupled analysis, supports and piping, and to see the impact of the supports on the piping analysis. So here the usual way to display the stresses, the reactions, and so on. Okay? And that's it. So a few words of conclusions. In fact, we are pretty proud to say that MetaPiping is for the moment the only software to offer the full implementation of the RCC-MRx code. If you look at the market, the software market, there are also the software that pretend having the RCC-MRx code, but in fact, if you look at the details, you will notice that it's a partial implementation. For example, only type P damage. Here we are the only that offers the full implementation from type P to type S with and without creep. Okay? And I hope I convince you that MetaPiping is a must-have tool for you if you are involved in the design of high temperature reactors. But in addition to the calculation capability, we have focused the development on the user friendliness. So it's pretty easy to use for new engineers entering the nuclear industry, so that's pretty easy. And what is very important too is the interface between MetaPiping for the piping analysis and MetaStructure for the support. So we are able to offer a coupled analysis, piping and support, to take into account the flexibility and the inertia of the support. So that's something brand new, in fact, that we are quite pretty proud to offer. The FEA module I showed to you is another important asset. For the moment, we are limited to the evaluation of the plastic moment, so the limit load, but this feature will be increased, extended in the next version. Okay? So that's it for the presentation. I would like to thank you for your attention. And if you are interested in a demo and further details, you can come to our stand, B009, and you are very welcome. I will be pleased to help you. Okay? Thank you.